Okay, so good day, everybody, and thank you for attending the full displacement hazard laboratory talk. Today, I'm very happy to have Francesco Visini as the speaker, and Francesco is a researcher at the Italian National Institute of Geophysics and Volcanology. Well, his research focuses on seismic hazard and fault displacement hazard assessment. He's an expert in fault-based PSHA, and he was also involved in the new seismic hazard map of Italy. Today, we'll speak about fault displacement hazard and his latest research, which was published just a few weeks ago. And the talk title is Rank-Dependent Empirical Regressions for Distributed Faulting of Deep Sleep Earthquakes. So, Francesco, the floor is yours, and
Thank
at
you.
the end, we will have a Q&A session.
Yeah, perfect. Thank you, Francesca and Paolo, for inviting me in this talk. Okay, I hope you can see my screen. So, of course, I'll be the speaker, but this kind of works, the empirical regression for distributed faulting is a topic on which we are working in the last, I think, 5 years with some people, mainly with Paolo, Alessandro, Una, Fia, Stefan, and Bruno. And so I will present basically, as Francesca said, the results we have recently published in a paper Visini et al. Is in a special volume of earthquake spectra, and many of the figures that are part of the test are taken from these four main papers. And just to be sure that I know probably we are all experts about what we are talking when we say fault displacement, but these are primary tectonic origin effects when we talk about in general of earthquake surface effects, and in particular the fault displacement hazard deal with principal fault rupture and distributed fault ruptures. In particular, in this talk, I will speak about the distributed fault rupture displacement hazard. Surface rupture, the definition is mainly derived by Youngs in 2003, and the main definition is about principal or primary faulting, that is the slip that occurs along the main plane, and the distributed secondary faulting, the displacement that occurs on other faults, shears, or fractures in the vicinity of the principal rupture. In the map in the center, we have the Norcia earthquake in particular, but can be generalized to any kind of surface rupture map, where we can recognize the principal fault with the trace in red, and the distributed faulting that are the traces in blue. On the right, we have a beautiful 3D block drawn, I think, by Paolo Boncio mainly, and where we can see in 3D what can be the relationship between the principal fault and the other distributed fault rupture. Just to say that these distributed ruptures can occur close to the principal or at a certain distance from the main fault, also to arrive to several kilometers from the principal rupture. Okay. So the first question is what can be inferred if we look in some way at the geological, the structural relation we have between these distributed secondary ruptures and the principal primary rupture. One of the last example of surface rupture has been also occurred during the Norcia earthquakes, where we have a tunnel that suffered of a displacement And this tunnel is about 8 kilometers away from the principal fault. Investigating the relationship between the seismicity, mainly the seismicity along the fault, the fault planes, the main fault plane, the principal fault planes, and the faults that discovered along the tunnel. There is Galli et al. In 2019 discovered, say that there was probably an antithetic fault that that is a pre-existing fault beneath the tunnel. And during in the last years, a group of geologists start to think about if it could be possible in some way characterize different typology of distributed ruptures. Basically, the three main questions were if are there different typologies of distributed ruptures, do they behave differently, and if the displacement on them can be modeled with different displacement attenuation function. So the starting point for our works on regression is the SURE database. This is the second release. It has been released in 2022. First, the SURE 1.0 has been released in 2019, 2020 probably. But with the SURE database, we have this possibility to categorize the distributed rupture into different typologies that the authors called rank. So during my talk, I will say different numbers for the rank, and a brief explanation will be given later. Of course, when the geologists, the authors of the database, try to categorize, to rank this distributed rupture, it's clear that a certain degree of subjectivity is necessary. So again, in the tree block I showed before, we can see now the same line but colored, the same ruptures, but colored with different colors. Okay, the principal fault are always marked in red, and this is a picture of an example of principal fault. Then we have a set of small secondary discontinuous, sometimes we can say short with small displacement, with no geological evidence. I don't know why. No geological evidence, not mappable before the earthquakes, colored in blue, that the authors rank as with the number 2, rank 2, or sometimes called simple. Then we have these primary distributed ruptures, or ranked as 1.5, that are some pre-existing secondary faults that can be, for example, splay of the main fault, sympathetic or antithetic splay of the main fault. And what is very important is that this secondary fault should have long-term geological evidence. And so in this way, in this sense, they can be mapped before the earthquake occurrence. And then we have the ruptures that occur far away from the main faults that are called triggered sympathetic distributed ruptures. So basically, in the case of a normal faulting, we have rank 1 for principal fault, rank 2 for this simple secondary discontinuous short small displacement, as we want to say, ruptures, 1.5, rank 1.5, that are longest secondary ruptures linked to the main fault, and rank 3 that are everything that is far from the principal fault, with picture of example. The fault displacement, the probabilistic fault displacement hazard, use, of course, a methodology that is quite similar to the probabilistic seismic hazard assessment. So in some way, has to characterize the seismic source, define the probability of surface rupture given a magnitude. This is something different from the PSJ classical approach. Then we have a probability of surface rupture at a specific location. And we can subdivide in two cases. If we are interested in, for example, to investigate the probability of surface rupture on a location that is on the principal fault, or if this site is away at a certain distance from the main fault, and in this case we talk about probability of distributed ruptures. Then we can model the fault displacement, so in some way try to quantify the expected amount of displacement, again along the principal site, for example, located along the principal fault, or for a site that is not located on the principal fault. So again, we are trying to model the expected displacement on this distributed rupture. And in particular, in this talk, but in the paper we published, we are interested in modeling the probability of surface rupture, of distributed ruptures, and of the fault displacement model. The first thing is to try to characterize the frequency at which the various rank we have in the database occur at the distance from the principal fault. So in the graphs on the left, we have this frequency distribution for normal earthquakes, and on the right we have the reverse earthquakes. With the colors, we have the different ranks. So if we focus on the rank 2, or simple, with the blue one, we can see the graph on the top are for distance from the principal fault that goes to several kilometers away from the far faults. And on the bottom, we have a zoom of the graph on the top, focused in the first 1,000 kilometers in the footwall or in the hanging wall. What is clear is that we have both in normal and reverse. We have an asymmetric distribution of the frequency of occurrence. For example, we have most measure for normal earthquakes is in the hanging wall in respect to the footwall. We have overall, for all the kinds of rank distributed ruptures, we have an overall attenuation with distance, and this attenuation seems to be stronger in the footwall than in the hanging wall. So, for example, if we look again at the zoom, we can see that, for example, the rank 2 attenuate with the distance, and basically this frequency goes below 10% at 200 meters distance in the footwall. In the footwall, the same percentage we can find at a distance of more or less 400 to 500 meters in the hanging wall. And another interesting thing is that, for example, the rank 2 typology respect to the other rank 1.5 or 21, 22, or 3 dominates the near fault. So we can see here, the blue, but also for the reverse is the same case. The blue curve is much more higher than the others one. And instead, if we go at several kilometers far from the principal fault, for example, if we go here, we can see that we have only rupture classified as rank 3 that are, just for you to remember, that are pre-existing mappable fault. So, basic on these evidences, we tried to model the probability of occurrence of these distributed ruptures. We used a logistic regression where that is function of the magnitude of the earthquake, of the distance from the principal fault, and of the hanging wall or footwall location. And we worked for different combinations. So we tried to model the probability of occurrence of rank 2 distributed rupture respect to the principal fault. So here in the graph, we have with each line, we have the probability of occurrence of at least one distributed rupture of this kind of rank at a given distance for a given magnitude. Just some examples. So of course, because these regressions are based on the data I've showed before, we have in the hanging wall probability higher than in the footwall. And so this is the first combination. The second one is that we call it combination C, is the probability that a pre-existing fault, primary distributed rupture ranked as 1.5, can be reactivated at a certain distance, again as a function of magnitude and distance and hanging wall or footwall location. The last thing important is that this kind of rupture can have their own rank 2 distributed rupture. So in this case, we try to model also the occurrence of these secondary simple distributed ruptures, but that are linked to the 1.5. So at the end, we have three combinations. Combination A, rank 2 to principal fault. Combination C, everything that is pre-existing, different from rank 2 to the principal fault, and the combination B, that is a subset, the probability to have a rank 2 simple ruptures that occur in response to a 1.5, for example. We tried to compare our model of probability of surface rupture with data published work. And so we used the Ferrario and Livio 2021 probability using they defined two models, what they call a regular and conservative scenario with the Young's et al. 2003 equation with two different equations, and this work. Of course, we used the same magnitude and the same grid size. If we look, for example, at the site of dimension of 100 meters, we can see that our model tries to distinguish between what is near and what is far fault. We used in the paper we published, we used a threshold, and as you can see, there is an abrupt variation of this probability. We are working on try to in some way smooth this change, but at the moment this difference try to reflect the observation of the frequency of occurrence of this kind of rupture. What is also important to note is that in our model, that is called this work in the graph, we worked only on rank 2 distributed rupture, so something a little bit different respect to the other equation, and this is probably the reason why our values are lower than the other, because the other models do not rank the distributed rupture. So if we move to the fault displacement model, the first important thing is that on what kind of measure we are interested. Of course, there are a lot of measures. We have the net slip, net horizontal, and long dip, and so on. But we have seen that the vertical or slip component or throw is the measure most often available for the surface ruptures of deep slip earthquakes, both for principal fault and distributed rupture. So in our paper, we used the vertical slip as the reference metric for our equation. So the first thing is to compare, is to have a look to the data, and we organized this graph in this way. On the left, for the graph on the column on the left, we have the distribution of the throw measured on the rank 2 distributed raptor as a function of distance respect to the principal fault. And we compared the throw of the distributor against the distance. We compared the throw of the distributor against the magnitude of the earthquakes, and again the throw of the distributed against the throw of the principal fault. So on the left we have the combination A, and on the right the combination C, that was the occurrence of the probability of rank that are not different to 2, what is for all the faults, all the pre-existing and mappable fault. So as function of distance, magnitude, and displacement. The colors identify the various earthquakes in the database. For each of these graphs, we can see some peculiar features. For example, in the first 2 graphs, we can see that the displacement on the distributed raptors attenuates with the distance from principal fault, both for rank 2, or what we say simple, or complex distributed raptor. Again, we see a stronger attenuation in the footwall compared to the hanging wall. Respect to the magnitude, we can see that there is a general positive relation between the displacement that we observe on the distributed raptor and the magnitude of the earthquakes. And something a little bit more complicated if we compare the throw on the distributed versus the throw on the principal fault. If we look at the simple distributed raptor, we can see that most of the data are below the one-to-one line. But if we look to the pre-existing fault, we can see that there are some data with a throw that is higher on the distributed raptor in respect to what occurred on the principal fault. Then this is something that should be investigated, try to understand the reason of this behavior. This is for the comparison, the look at the data for normal earthquakes, and this is for reverse earthquakes. We can see more or less the same behavior. Reverse earthquakes contains less data, so some of the graphs are not so explicative as for the case of normal fault. But again, what is interesting is that we have this attenuation for the simple distributed raptor. This attenuation is not so obvious for the complex distributed raptors. And again, also if we look at the displacement in the last line, we can see that simple distributed raptors has throw basically below the one-to-one line, but combination C can show distributed throw that are higher on the distributed respect to the principal. So using this relationship, we tested different models, but at the end we verified that this is the model that best reproduce our data. So to predict the median value of vertical displacement on distributed raptors, we can see that this value is a function of distance, function of the throw on the principal fault, of the magnitude, style of faulting, location, hanging wall, fault wall, and we also calculate the different coefficient that is a function of the combination we are interested to model, simple respect to the principal, or complex respect to the principal, or simple respect to a pre-existing fault that is not the principal one. And we can have a look to the resulting median throw for normal and reverse fault using the resulting equation for the 3 combinations. So each line on the top we have simple to principal. In the center we have the combination B, the simple to the pre-existing fault, and in the third line we have the pre-existing respect to the principal fault. So the first common feature is that we have a rapid decay in the near fault. As you can see, in the first 100, 200 meters, we have a rapid decay of the median value of the vertical displacement. The colors of the line are same magnitude and different throw on the principal fault, but the same behavior is if we change the magnitude. The second feature is that we have a median vertical displacement that is higher in the third line, given the same magnitude than throw on the principal fault, is higher in the third line respect to the first. So we are modeling a displacement, an expected median value of the displacement that is higher if a pre-existing fault exists beneath the sites of interest. And the third common features is that we have a slightly higher value of median for reverse fault respect to the normal fault. To say, I say that we find the best model that approximate the data. So to find, of course, the model, we did some tests, and here I want just to show you the results in terms of residual data for normal and reverse. The optimal will be to have this black line that is basically 0, and of course we are very close to 0, but if we fuse all data. But if we go inside the details of our modeling and we see this the baseline of the regression for the different combination, we can see that we can still work to improve this kind of regression. It's not only a problem of modeling, but I would suggest that it's also a matter of database population. Of course, more data will be available, better will be the resulting regression we can do. And here is a comparison of the predicted median value and standard deviation respect to the observation for the North Char earthquakes. For the 3 combination, we have with the red circle. We have the observation, and with the black square we have the median predicted value, and the gray bars are the 1 sigma, 2 sigma, and 3 sigma. And of course, we cannot expect that a single earthquake to have prediction and observation perfectly in line. This is something obvious, but we can also see that the scattering in the observation is something that we are trying to reproduce, and I think that probably the introduction of this value of the mean vertical throw expected modeled on the principal is something that could be much more refined and investigated to obtain a better prediction. We can discuss this later with a question, of course. So the last slide is how to use this different all this work about ranking and different probabilities of occurrence and so on, because at the end the goal of the PFDHA is to calculate the hazard at a specific site. So we created this decision tree algorithm, is an example. And we use it just as an exercise. We use an earthquake with a magnitude 7. We place this site at a distance of 2 kilometers in the center of the fault. So the first decision we have to take is, can a pre-existing fault, complex fault, be precluded beneath the site? If the answer to this question is no, then the hazard at the site should be given by the sum of the conditional probability of exceedance computed for all the 3 different combinations. So we can have reactivation of a pre-existing fault. We can have the occurrence of simple ruptures due to the principal fault, and we can also have the occurrence of secondary distributed ruptures in response to this pre-existing fault. So if we look at the hazard curves, we have the conditional probability of exceedance with respect to the throw. We do not have the frequency of occurrence, so it's just a probability of exceedance. So we can see that the total hazard, the red curves, is given as the sum of these the 3 combination. If the answer to this first question is yes, because we have some, I don't know, some trenches, some geological data so we are sure we can exclude the pre-existing fault beneath the site, but we cannot preclude the presence of a pre-existing fault at a certain distance, more or less 1 kilometer from the site, then the total hazard will be given by the sum of the occurrence of simple ruptures due to the principal and to the pre-existing fault. As you can see here, there is a great difference in the 2 red curves. And it's because the total hazard in the first case is mainly dominated by the reactivation of the pre-existing fault. Finally, if also the answer to the second question is yes, then the total hazard is simply given by the conditional probability of exceedance computed for the combination So just the occurrence and the amount of displacement expected for a simple rank 2 distributed rupture. So going to the conclusion, we have seen that distributed ruptures have different characteristics, and also that the occurrence and displacement of distributed ruptures depends on ranking. What is very important is that the rank 2 distributed rupture mostly control the hazard in the near fault. Instead, rank different from 2 dominating the far fault. And what is very important, if a pre-existing fault exists at the site, this fault dominate, the activation of this fault dominate the hazard. So at the end, the conclusion is that rank-specific regression could be combined depending on the tectonic setting and level of geological knowledge of the site. Some perspective, not at all, not a lot of point, just because focused on this kind of works. Of course, there is a lot of work to do and investigate how to deal with spatial incompleteness of the database, along strike and cross strike. We use a very simple metric. We use a distance between the point and the fault at surface. Can we use something better? Rupture distance or something similar as in PSJ. Of course, regression can be improved, and yes, of course. And 2 days ago, I was writing. I wrote this point. If a rank different from 2 exists at the site, they dominate the hazard. Sorry, I repeated this 3 times. So the point is that we have to refine, we have to work to better analyze how to calculate the probability of rupture reactivation. And it's interesting that yesterday I saw this paper published by Francesca, Livio, and Leonello, prediction of seismic rupture location from fault maps. And I didn't read the paper, but I just copy 2 statements from the abstract. We investigate whether geological maps could be exploited in the course of other assessment. And we suggest that specific regression which consider available fault maps could be applied to compute the probability of occurrence distributed faulting. I think we are going, I hope we're going in the same direction. And as we have seen here, the presence or not of a pre-existing fault completely changed the hazard curves. So I think this is a very important topic to be investigated in the future. Thank you. I've finished. Cannot see you, but
thank you, Francesco, for the very detailed but also clear presentation. And well, now it's time for the Q&A session. So if anyone wants to unmute or to type into the chat.
Hi, Francesco.
Hi, Julia.
Let me the first one because I have to leave in 10 minutes. So I think very interesting presentation. I love it. My question is about how maybe there's few earthquakes controlling the data, the catalog, particularly in the reverse faults. There's a slide, I think it's number 20. Is that the colors refer to different events?
Yeah.
Yeah. And so, I mean, this is something it has to be at least pointed out. I think that maybe because that means that new data coming would probably change completely the regressions. No, I mean,
I hope no. I hope no, but you are perfect. You are right. Yes. Yeah. Yeah. Here we can see, for example, for the reverse, we have more or less the same number of earthquakes, but very different numbers of measure. So, for example, if we look at combination B, we have few points. So not sure, but also if you look at the old data, we can see that these earthquakes basically dominate the regression from 2,000 kilometers distance from the principal fault to Serbia. Yeah, you're right. I think that can be a problem, and it's also, when I say a problem of completeness, also because it's possible that at a certain distance from the main fault, we just have only measure that are higher than, I don't know, let's say some centimeter, 5 centimeters, just because who surveyed the earthquakes didn't care about 1 centimeter at 1 kilometer's distance. So it's a problem of bias and completeness, and also, as you said, of population. Yeah, you're right.
Yeah,
I hope that will not change too much, but
No, I think it's amazing work, but I thought it was something to comment on, I guess.
Yeah.
Thank you very much.
Thank you, Julian. Thank you.
Please, Alex. Well, I saw you raised your hand, so you can ask your question, maybe.
No, maybe just.
Okay, now you are
I'm
unmuted
sorry.
now. Okay.
My first day using this, apparently. Thanks so much, Francesco. What a great talk and a great paper. I really enjoyed reading it, so it was nice to kind of hear the review as you say it. I did have a question on how the combinations are combined in the hazard curve. I forget what slide it was. It was maybe just before the conclusions. Yeah, that's a perfect one.
Yeah.
So in case 2, we're considering the situation when our site in gray can have a distributed rupture that's caused by the primary fault or the rank 1.5, right?
Yeah.
Yep. So can the rank 1.5 generate its own earthquake?
The rank 1.5 could also generate its basically should not, because if I can go
I think it should not, right? It says your daisy chaining, as we would, that's maybe a local phrase, but your daisy chaining displacements from the principal to the 1.5 and then the distributed. So I think if it can't generate its own earthquake, it is the same earthquake rate, 2 millimeters a year or whatever, maximum 2 millimeters a year that comes from the red fault. In that case, it seems like the curves should be added on the x-axis, not the y-axis. You might still have different y-intercepts because you have different probabilities of rupture, but the summation, when you sum on the y-axis, it means independent source, I think.
Okay, if I correctly understood. If we assume that also this the yellow line can generate earthquakes, right?
Does it have a different slip rate?
Yeah. In this case, we are just saying, okay, if an earthquake occurs on the principal fault, we have, let's say, 70% of probability that the yellow will be reactivated. So we are saying if we have 1 earthquake every 10 years, we have here 0.7 earthquakes for 10 years. So
that's why the y-axis is different on the black lines.
Yes, exactly. It's a matter of exactly of this probability and also of this, and this is why they intercept at a certain point. But we cannot sum along in this way. No, you mean along the y-axis, because it means that in that case you are saying summing the displacement. A rupture can be a sum of 2 different sources. But we do not have this information in the database. When we measure a throw in a database of a distributed rupture, we are saying it's the coseismic measure of linked to a single source.
Does it have to mean that it's?
Yeah, this is why
the exact point. I mean, that's like in a Pisha curve when we have a ground motion value. We don't say, oh, this is like 3 different earthquakes that happened at once that cause it. It doesn't have to be simultaneous. You're just counting the number of times this displacement in this area in our gray box.
And this is exactly the same, because the sources are treated always as independent, because each source has its other curves. Like in PSJ, we sum the probability. That probability can be that level of throw, in this case, a level of throw in PSJ, a level of, for example, PGA, can be exceeded due to the occurrence of an earthquake located here or an earthquake located here. So you sum.
They're different sources, so that's why you sum on the y-axis. Because they're different sources.
And in this case, it's more or less the same, because at the end you are saying, okay, the yellow one is conditioned to the occurrence of this. But we are just reducing the probability of occurrence with the probability, with saying, okay, we have a 70% of probability to be activated. You treat them as 2 independent sources.
Alrighty, thank you.
Oh well, we can. It's better if we talk with with drawing something. Probably.
No, I just it's still a little bit early here. I have to wrap my head around it. It's late there, but I appreciate talking through it. I've had that question, so thanks so much for talking through it and explaining it to me. Maybe I'll have to email you with a question if I can't figure it out now. Thank you.
Thank you.
Okay, Francesco, we have a question in the chat. I can read it aloud if you cannot get it. So it's by Stephen Jeffrey Brooks. Okay, since we are evaluating the displacement, can the obtained models be compared with the insert time series analysis from the different folds?
Tony, can you repeat the question, because I was looking for the chat, and if we can compare the resulting hazard
Of
level
your
with
study with the insert time series.
I don't know because I'm not an expert of INSAR, but we are generating probability. So it's possible that we can use the INSAR in some way to populate the database. I think that there are some papers about this, but I'm not sure that our other curves could be used and compared with the INSAR data, because we are talking about finite displacement along single structures more than INSAR displacement, probably. I don't know, probably, Francesca, you are more expert than me in this case.
No,
Probably.
actually, I don't even have an answer.
We could predict. We could text.
We could think about that. Yeah, that's an interesting point. Yeah.
Yeah, good point. Yeah.
Okay, so I have another question for you, which is before we have the question you have addressed. So the definition of rank 2 or 1.5 is critical for the models.
Yeah.
So how sure are we that we can properly define if a fault is 1.5 or 2?
This is the same question I posed to the authors of Sure, and let's see. And no, basically they are quite pretty sure that you can define it, because this primary, the rank 1.5, for example, should appear with this field. They are much more longer than the distributed one. And I'm sorry, I do not have a map of this, but much more longer than the other one. And sometimes you can see they are linked with the principal. Or, for example, you can have antithetic or synthetic space. So, of course, it's based on, in the case of North Channel, it's easy because you have the seismicity here that can, imagine the fault plane. And but I think that they did great work of revising the geology, the structural geology of the site for each of the faults in the database. Of course, the problem is much more, in my opinion, is much more on differentiating between rank 1 and rank 1.5. Because in that case, sometimes it's not so obvious that is not the principal fault. But from rank 1.5 to rank 2 probably is quite, the definition can be given by different authors, I think is more or less the same, should be more or less the same. But I don't know if Paolo or some other authors would say something about that, if they are still alive.
Yes, if I can maybe I can add something about the question by Francesca. So that's a very good question. So I worked on the Sure database for ranking. So how to distinguish between rank 2 and the rank 1.5. So we asked, working on the database, we asked, okay, this is the primary. Oh, okay. And the others are distributed. For one distributed rupture, the question was, is there any evidence that this rupture was activated also before? I mean, is there any evidence, any geomorphologic evidence, for example, a scarp, or a geologic evidence, for example, a offset of geologic unit recognized on a geologic map along that rupture? So in other words, could it be possible to map a pre-existing fault there before the earthquake? So if the answer for doing that, we went back to existing geologic maps of the area, or also we had a look at how to say Google Earth to look for scarps indicating cumulative displacement. So any evidence of pre-existing pre-event displacement. So in the end, if sometimes there are very good maps of coseismic ruptures distinguishing between rupture on previous compound scarps. So we use it, in that case, we know that the rupture reactivated something already activated in the past. So if the answer to that question was yes, the rank was 1.5. If the answer is no, because maybe we don't know, but we have no evidence for a mappable fault, the rank was 2. Rank 2 doesn't mean that it is necessarily a newly formed rupture. Can be a jointing reactivated, can be a fracture, a fault, but you have no evidence. So and we rank it as a number 2. But in general, rank 2 are a small rupture very close to the principal one. So this is the main, the main criteria that guided us in ranking.
Yeah, in some way, just thinking is as we can say, okay, the rank 2 are really what we call distributed, and probably this can be in some way defined as localized, because they occur where something was mappable before the earthquake.
But yeah.
Yeah.
Mainly the aim was to distinguish what can be differentiated from rank 2, from all distributed. Okay. I hope I answered your question, Francesca.
Yeah, definitely.
But of course, that is one of the most important points, because at the end, when you distinguish different distributed ruptures, the regression change. You can see here, if you model everything with no rank, you can arrive to have some probability at the distance of tens of kilometers. But if you use the rank, the rank 2, the probability at the distance larger than 4 or 5 kilometers is basically 0 in the case of normal or reverse earthquake. Yeah. So that is is an important point at the end. Yeah.
Okay, so is there something else? Let me look at the chat.
Mm-hmm.
Okay, we have again Steven. So Steven, if you want to join the FDH Lab, just send me an email and I will add your address to the mailing list. And well, his idea is to try to define the behavior of single faults with the fault-based approach. And he also thinks he could help in populating the dataset, but okay, maybe the probable displacement you obtain can be in some way compared. Okay, so that's another avenue for eventual future collaboration, and we are happy to enlarge our horizons, of course.
Yeah, I agree with you.
Okay, so if there are no other comments or questions, I thank you, Francesco, for the very good talk. And I recall we will have another talk on April 10, I think, or 9, I don't remember actually, by Octavi Gomez. And in a few days, this talk will be on the YouTube channel, and I will send you all the link.
Perfect.
Thank you, Francesca.
Thank you.